So after all that, then, what is the law of conservation of energy? It says this: energy cannot be created nor destroyed. You can only transform it from one type to another. What this means is, Darman, if we're looking at a closed system where there's no outside sources of energy, it's not plugged into a power outlet, we're not adding gasoline. If we're looking at a closed system, the total amount of energy at the start and the total amount of energy at the end must be the same. There's a more poetic way to say this. The more poetic way says the total amount of energy in the universe has remained constant since the Big Bang. We look at an example. Both the KE and the kinetic energy and gravitational potential energy of a block sliding down a ramp are shown below at the bottom position. George, at the bottom, what's the potential energy of the block as a number exactly? What's the kinetic energy of the block? What's the total energy of the block? The law of conservation of energy says that anywhere along here, the total energy must be 75. So what must the potential energy up here be, George? As we slide down, we're losing potential energy. It's turning into kinetic energy. That's why the object is speeding up, because kinetic energy is the energy of motion. It's gaining kinetic. How much? What if we have 50 joules of kinetic energy? How much potential energy? Okay. In words, the law of conservation of energy, I tend to abbreviate it C of E, says the amount of energy of a closed system never changes. Nick, as an equation, your initial stored energy plus your initial motion energy has to equal your final stored energy and your final motion energy. Or, with symbols, kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. We can even be a bit more accurate, Kai. We can actually include energy loss to heat. Then it's going to look like this. KE initial plus PE initial equals KE final plus PE final. And whatever's missing must have gone into heat. A skate park is a really good example of conservation of energy. Now, I've just turned friction off. We're going to keep it simple. If I lift the skater up, what I'm really doing is I'm giving them potential energy. See? That's the blue bar. As I let them go, do you notice the total energy, the yellow bar, does not change? That's the law of conservation of energy. What we're having occur here is a transformation between potential and kinetic. At the bottom, what should my potential energy be exactly as a number? So my kinetic energy should be at its maximum. That's why you're going faster at the bottom of a hill. What about at the top? For a split second, I'm coming to a stop. I have no kinetic energy. Why? It's all potential. So we're giving you a different way to think about things, not in terms of kinematics and gravity and forces, but in terms of energies as well. Also can be thought of that way. Now, this is a simulation. In real life, you have some friction. I'm going to turn a tiny bit of friction on, and you're going to notice another bar slowly start to creep up. It's labeled thermal. It's heat. Is the total energy on the yellow bar changing, Sarah? What is changing? We're losing more and more energy to heat, and we can't get that back very well. This is the world that we live in. It's a world that's bound by the law of conservation of energy, and it's also a world that's bound by what we call entropy. We're losing energy to heat. typically in any process. Processes are messy and we lose to heat. Eventually, all the energy will have been bled off as heat, and that will have gone out into the atmosphere. Or for our universe, right now, every star is an oasis of energy, but eventually, a few 100 billion years from now, all of the energy in the universe will have spread out evenly, and the average temperature of the universe everywhere will be about 4 degrees Kelvin and no life. There's a famous poem by Robert Frost where he asks whether the world will end in fire or in ice. The universe will end in ice, most definitely. I have a marble energy transfer device. Aiden, could you... Oh, Aiden's away today. Oh, Aiden, if you were here today, I totally would have let you play with the marble energy transfer device. It's so sad that you're not here, Aiden. Another great example is bouncing a basketball. When you're bouncing a basketball, Mason, it has all gravitational potential energy at the top. That's why it's at rest. It has all kinetic energy at the bottom. It's not quite a closed system because you're adding energy with your hand, which is why you can get it to return to the same height, even though it is losing energy to sound and heat. In fact, all of you that have played basketball probably had the 8 a.m. Saturday morning Egg McMuffin game where the basketballs were so cold from being in the car, you have to pound them on the floor. You're actually adding heat to the basketballs and heating them up. Pile driver is another nice example of conservation of energy. Oh, good. Okay. Example 1. A projectile is launched straight up into the air. If its initial velocity was 75 meters per second, how high does it go? Ignore friction. I gotta be honest. If you just gave me this, I would use kinematics. I would say, okay, VI is 75. At the top for a split second, what's VF? I would use VF squared equals VI squared plus 280. But it says use energy. Okay, let's use energy. It's going to look like this. KE initial plus PE initial equals KE final plus PE final. Does it want me to include heat? Sarah, what does it say in brackets? Ignore heat. Okay. How do we calculate kinetic energy? Well, that was a half mv squared. So I guess kinetic energy initial is going to be a half mv initial squared. Plus mgh initial. And that's going to equal a half mv final squared plus mgh final. Then, Darman, I always ask, are any of these zero? Kinetic energy will be zero when we are at rest. Is this projectile ever at rest? At the top? I agree. Is that going to be initial or final? That's zero. Potential energy will be zero on the ground. Are we ever on the ground? And so this ends up becoming a half mv initial squared equals mgh final. Brea, is there an m in everything on the left? Is there an m in everything on the right? Turns out the m's cancel. That's convenient. Brea, what was this wanting me to find? So how would I get the h by itself? By? Yep. And we'll get this. H equals VI squared all over. I'll write it as 2G instead of, I'm not too lazy to write the 1 from the 1/2. Which is the same thing, same area you would have ended up with using kinematics. It's going to be 75 squared all over 2 times 9.8. And it gets to almost exactly 287 meters high. Is that right? Yep. Okay. And again, I wouldn't use energies probably for this question. I would use good old physics 11. VF is 0, VI is 75, A is negative 9.8, VF squared equals VI squared plus 2AD, solve for D. But part B, I'd have to use energy. It says this: suppose the projectile only reaches a height of 125 meters, not 287. How much energy was lost to air friction on the way up? Or how much work did air friction do slowing the object down? How much energy? This is a job for conservation of energy. It's going to look like this. KE initial plus PE initial equals KE final plus PE final. But this time, it looks like they want me to include the energy that we lost to heating up the air. Are any of these zeros? Well, potential energy will be 0 when we are on the ground. Are we ever on the ground? Are we starting on the ground? Yeah. So you know what? PEI is nothing, right? PEI is not a real province, please. Calls themselves a premier. They're a mayor at best, right? It's a city, not a province. Is PE final 0? Nope, it's up there. What about kinetic energy? Are any of these going to be 0? Kinetic energy will be 0 when we are at rest. Gabor, what did this question want me to find? How would I get the heat by itself? I'm glad you made that silly mistake. This is a weird one. For some reason, every year I see several kids that look at this and they say, I'll divide the PEF over. Gabor, what's the PEF clearly doing to the heat? So how will I move it over? And I haven't figured out why that's such a common mistake, but it is. Don't do it. Hopefully you won't do it now. I'll damage your self-esteem if you do. So it's going to be KE initial minus PE final. The amount of energy we lost to heat is going to be a half mV initial squared minus mgh final. Brea, is there an m in the last term? Is there an m in the middle term? Is there an m in heat? Is there an m sitting there? So do the m's cancel here? No. But we can plug and chug. It's going to be 0.5 times what was m? 12 and 75 squared minus 12 times 9.8, not negative 9.8, we're in Scalarville, times, the height that we got was 125 meters, not the 280 or whatever it was. 287. 0.5 times 12 times 75, don't forget the squared, minus 12 times 9.8 times 125, I get 19,050. Cool. Braden, what does C want me to find? What? Say that again? I mean, I might be tempted to go, don't write this down, but that M, that would have to be the mass of the air. Do I know the mass of the air? What did I find in part B? What did I just find, Braden? When in doubt, ask, especially if it's a part C, ask yourself, hey, maybe I'm going to use my answer from part B, right? Maybe what I'm going to use is just what I found. What did we find in part B? What else did I call it in brackets? No, I did not call it air friction. I used another very important physics word in front of that. No? What? What? How do I calculate work? Work equals force times distance. Braden, I'm going to argue then maybe the work done by air friction will be the force of air friction times distance. Do I know the distance? 125. Do I know how much work air friction did? Hey! How would I get the friction force by itself? It's going to be 19,050 divided by 125. Now this is an average force because as the object slows down, air resistance is getting smaller and smaller, and we can't deal with a changing situation like that without calculus. And I get an average air force of friction of 152.4. I'll call it 152 newtons. I wrote here, Mr. Dewick has a very cool demonstration of the conservation of energy. I do. Sorry, Aiden, you're not here. So, when do I use the law of conservation of energy? Well, I've always tried to give you a bit of a trigger, or is there a projectile T-table? Forces, mu, free body diagram. When am I going to use conservation of energy? When there's a change in height, when there's a change in speed, and especially if there is a yucky, curvy path, then you want a scalar-based approach. Okay? Let me give you an example. I like example 2. I like example 2. Example 2 is a nice question. At location Z, a skier is traveling at 18 meters per second. How high up the next slope can the skier reach if we ignore friction? First of all, is this question asking how much work? Be obvious. So this is not a force times distance. Well, here's the skier. Here's where they're going to end up. Is there going to be a change of height and a change of speed and the yucky curvy path? Conservation of energy. So Ke initial plus Pe initial equals Ke final plus Pe final. Did I give you this on your formula sheet? Yeah. But I don't think I gave you the one with heat attached. I think that I'm going to ask you to remember to add if it says include heat. All right. Are any of these zero? Potential energy is zero when you're on the... Oh, you know what? Let's put a little initial there, and I think final is right there. Yes? Potential energy is zero when you're on the ground. Are we ever on the ground? Where? Yeah, PEI. Come on. The afterthought of the provinces, right? Is kinetic energy going to be zero? Kinetic energy will be zero when we're stopped. At the top. So I get this. A half mv initial squared equals mgh final. Oh! Brea, is there an M in everything on the left? Is there an M in everything on the right? Can little kids and grown-ups ski together and hold hands, or does the grown-up constantly have to be adjusting their speed because their mass is different? They can ski together and hold hands because M cancels. Convenient. What are we trying to find? How would I get the h by itself? Oh, Freya told us a few minutes ago, divide by g. So height is going to be v initial squared divided by 2g. It's going to be 18 squared divided by 2 times 9.8. And I get 16.5. Suppose it takes, yep. My answer, oh, my units are wrong. Thank you, Kai. Meters. I owe you a candy, don't let me forget. Suppose, oh, I like example 3. I like example 3. Example 3 is the next question. Suppose it takes an average force of 245 newtons to pull the bow back a distance of 68 centimeters. Well, first thing I would do, Danica, is cross out the 68 and make that a 0.68 meters. Nice try. Okay. Danica, what's A want me to find? Well, my first thought is, does force times distance work? Did they give me a force? Yeah. Did they give me a distance? Are they in the same direction? Yeah. It's going to be 245 times 0.68. I'm going to keep all the sig figs here. 166.6 joules of work. Where'd that energy come from? The archer lost some energy, some food energy, when they pulled on the bow. That energy is now stored in the bow. How much potential energy is stored in the bow? A common mistake kids make is they see potential energy and they think, don't write this down, oh, it's got to be mgh. Are we lifting this bow in a vertical direction? It's not mgh. You know how much energy is stored in the bow? The amount of work that we just did. So because we know how much energy is stored in the bow, we can then figure out how fast the bow will leave. If the arrow has a mass of 42 grams, nice try, Duick. Zach, 42 grams, how many kilograms? 0.42 or 0.042? Good stretch. Good. How fast should it leave the bow? Here, I don't have a change in height or a change in speed, but I definitely have work and energy, and they're asking how fast. I think this is a job for conservation of energy, G. So it's going to look like this. Initial plus initial. And it doesn't matter whether you write kinetic first or potential first, but it's initial plus initial equals final plus final. Okay, are any of these 0? Is the arrow ever at rest? Braden nodded. Where? At the beginning or after? If it was gravitational potential energy, I would say, are we ever on the ground? This is not. Do we ever use up or lose all of our stored energy? When you shoot the bow, so after. So what we end up with is this, 166.6, not mgh, didn't lift it, equals a half mv squared. Brea, is there an m in every single term here? So do the m's cancel here? Nope. Yeah, you know what? A heavier bow won't go as fast. Sorry, a heavier arrow won't go as fast. Lighter arrow will go faster. That makes sense. I want to get the v by itself. I think times by 2, divide by m, or divide by 0.5 m, whichever you feel comfortable with. Vf squared equals times by 2, divide by m, which was 0.042. Oh, that's Vf squared, square root. $89.1 meters per second. My Nerf dart gun works very similarly. When I pull this, I'm applying a force over a distance to store energy in here. And then when I pull the trigger, the stored energy turns into kinetic energy. Although I've actually calculated how fast this dart should leave. I've actually measured the force times the distance. This thing is only about 8% efficient. They're bleeding a lot of the energy off for safety. Oh. Projector. One of the best applications is roller coasters. Oh, I haven't got to roller coasters yet. When do I get to the next one? Sorry, spoiling the punchline. A model airplane flies horizontally at 22 meters per second. A says, calculate its kinetic energy. Well, that's easy. KE is going to be a half mv squared. It's going to be a half times 2 times 22 squared. I do this in my head because the 2 and the 1/2 cancel. It's going to be 22 squared, which is 11 squared, 121 times 4. 484? All right. Suppose the plane goes into a dive. By the way, when a plane goes into a dive, what happens to its speed? What happens to its kinetic energy? Kinetic energy. Of course it increases. Why? Because it's losing potential energy. Energy's got to go somewhere. Okay? So this also explains, you can think of why a plane speeds up in terms of forces and gravity, but you can also think about it in terms of energy. It's losing potential energy. It's got to gain kinetic energy. B says it levels off 40.5 meters closer to the Earth. How much potential energy did it lose? I guess it lost mgh. 2 times 9.8 times 40.5. It lost 793.8 joules of energy. All right. Xavier, how much kinetic energy did it gain during the dive?
793.8 minus 484.
We lost potential. Where did that potential have to go? So we just gained 793.8 joules. Thank you very much. No minus here, right? In fact, do you know what the new kinetic energy is? The new kinetic energy is going to be 793.8 plus the original 484. The plane now has 1,277.8 joules of kinetic energy. How do I calculate kinetic energy, Xavier? What's the equation?
1/2 mv squared.
Did the plane's mass increase when it dove? So what must have increased if we gained kinetic energy? The V. Not a one-to-one because of that squared. Okay. So E, if we ignore air friction, how fast is it going now? Can you look at the kinetic energy equation and can you get the V by itself for me, please? I'll give you a hint. V equals.
V equals K over M2M squares.
So, ready? Look up. You can either write KE over 0.5 M square root, or you can put the 2 on the top. That's acceptable, but you can't have the 2 in the bottom, because how would I move that 2 on the bottom on the right? Times it on the left. Is that okay? And then square root. Okay, so it's going to be the square root of 2 times 1277.8 divided by, was the mass also 2? Oh, that's convenient. So it ends up just being the square root of 1277.8 by a fluke. And I get 35.7 meters per second. And ballpark, that looks about right. How fast was it going at the beginning in part A?
22.
Is it picked up speed? It's going faster. It's not a one-to-one relationship, but that looks like a good answer. I think I'm going to temporarily pause here. We'll look at roller coasters next class, because why wouldn't we? But for now, I think you can try number 1. Number 1 is so easy that it's tough. If you look at number 1, at the very, very beginning, at section 1, what's the potential energy if we're on the ground? So you can fill that in. What's the kinetic energy? A half mv squared. Can you quickly on your calculator go a half times 60 times 8 squared? What do you get? 1920? And then ME is the total mechanical energy, which is potential plus kinetic. So also 1920. ME is like the yellow bar on the skateboard app that I showed you. It's never going to change. So 1920, 1920. What will change is your potential and your kinetic, but they have to add to 1920. There's enough information in here for you to fill in the blanks and figure it out from there. Okay? See if we can figure it out. Number 2 is good. 3 is good. If you're not sure how to do 2 and 3, because I haven't done roller coasters with you actually, just leave a gap and you can handle them. Try them later. You can skip 4. 5 is good. 6 is good. 7 is good. I skipped 4.